Welcome to my classroom. In this fuel cells and batteries courses, in previous lecture number 7, we have discussed about the thermodynamics of fuel cells. In this lecture number 8, we will discuss about what is the difference between a global reaction and local reactions in a fuel cells, where we are going to discuss about what are the elementary steps and non-elementary steps involved in the reactions that are occurring at anode and cathode. We will define what is Staffel reaction, what is Olmer reaction, all that. And we will little bit of more thermodynamics, what is equation of state, what van der Waals equation, what is ideal gas law equation. If a hydrogen cylinder is there, we have to determine the volume of the cylinder using those equation of states. Okay, so that's why it is important that we discuss about that. And we will discuss about some of the thermophysics and thermochemistry. What is the definition, like heat of neutralization, heat of solution, and what are the laws of thermodynamics, like Laplace law and Hess law, thermochemistry laws. Okay, then we will discuss about heat of formation, heat of the reaction, heat capacity of a gas mixture, Cp value, mean Cp value of a gas mixture, because we know the Cp value of individual components. If there is a mixture, how to determine the heat capacity of a gas mixture. Okay, then we'll discuss about what are the enthalpy changes associated with the chemical reactions. We'll discuss about heat of combustion, heat of evaporation, what is hydrogen higher heating value and hydrogen's lower heating value. Okay, then enthalpy and entropy of formation and the effect of temperature. All that we will discuss in this lecture. Okay, ready? In a fuel cell, when we will say a complete circuit is formed, when we have all the components are present. What are the components present? Let us see. Okay, let us start with this global reactions and local reactions that is taking place at anode and cathode in a fuel cell. Okay, a complete circuit is formed when all the components are in place under proper conditions and continuous flowing current of ions and electrons can be maintained. Okay. See, what are the components that are involved in this fuel cell operation? The components that during the reaction that are involved are, we have anode, cathode, we have electrolyte, and we have external connection between the electrodes, because current has to pass through it and electron has to pass through it. Remember, the direction of electron and the current are in opposite in direction. Okay, and any absence of any of these components will be lead this to open circuit. Absence of any one thing will lead to open circuit, that is no flow of current. When we will have a situation of no flow of current, any one of the above is absent. If any one of the above is absent, in the previous lecture we have seen what is the reaction that is taking place at the anode and the cathode, right? So off cell reaction at the anode, off cell reaction at the cathode we have discussed. So we know that if hydrogen is used as a fuel and oxygen is used as the oxidant, we know what is the reaction that is taking place at the anode, that is hydrogen becoming 2H plus ions plus 2 electrons, right? And similarly the off cell reaction that is taking place at the cathode is given by that the 2 electrons will be going through the external circuit and reaching the cathode surface. Similarly, the H plus ion formed at the anode will be passing through the electrolyte and reaching the anode cathode surface, and oxygen is entering into the cathode surface. So equation with the reaction that is taking place at the cathode is given by oxygen O2 plus 4 electrons plus 4 H plus ions, giving a reversible reaction forming 2 molecules of water, 2H2O. Okay, so that way the overall reaction is given by H2 plus half O2 giving H2O, which is again a reversible reaction. Okay, so we have open circuit condition. Okay, So what is the reaction that is taking place? Global reaction. What is global reaction is? We know that. What is the global reaction taking place at the anode and cathode? We have seen that one. The heat of the reaction is when the reaction is taking place, that H2 plus half O2 giving H2O, associated with it we have some more products being formed. Okay, that is heat, then electricity. Okay, that the H delta H we need to know, that is the enthalpy of a chemical reaction, or we can say heat of a chemical reaction. It is nothing but the difference between the heats of formation of the products and the reactant. How we get the delta H of the reaction? Delta H of the products minus delta H of the reactants will give us this thing. Okay, so delta H is equal to delta H of products minus H of reactant. So in this case, we have one product and there are two reactants. So water is the product. So delta, sorry. So water delta H is equal to H of water minus H of heat of formation of water minus heat of formation of hydrogen plus of into heat of formation of oxygen. Remember respective moles that is involved in the reaction balanced equation that we have to consider also when you are writing that one. Okay, heat of the reactants minus heat of the products and heat of the reactants can be written that way. Okay, and well, you know what is the heat of formation of the pure elements? The heat of formation of the pure elements is 0, and heat of formation of water is around 286 kilojoule per mole if it is in liquid state at 25 degree Celsius. Similarly, you will have delta H equal to, how to find the, then if you know this value, delta H of heat of formation of water in liquid phase is minus 286 kilojoule per mole, and heat of formation of pure elements hydrogen and oxygen are 0. So easily you will find out that delta H of the reaction is minus 286 kilojoule per mole. We know that if delta H is greater than 0, it is endothermic reaction. Delta H is less than 0, it is exothermic reaction. When delta H is equal to 0, it is no heat or no heat loss is there, right? Okay. So that way here we are going to get minus 286 kilojoule per mole, which means that it is an exothermic reaction, which means that heat is liberated from the reaction. Okay, or we can say, if we consider in thermodynamic term, we can say in a system, exothermic reaction takes place mean heat is released. Okay, the temperature is released, temperature of the surrounding will be rising because of heat is liberated out. Okay, endothermic reaction means what? It will absorb heat. That means that it will cool the surroundings if you are not having any jacketed kettle. Okay, so that way we can write for this overall reaction H2 plus half O2. We will write H2O, water is formed, liquid form it is formed. Then we will have H2O liquid plus 286 kilojoule per mole is what being done. Okay, then coming to this hydrogen's heating value. What is hydrogen's heating value? It is the amount of heat that may be generated by a complete combustion of 1 mole of hydrogen. What is that? Heating value is nothing but the amount of heat that is generated by a 1 mole of a substance. If it is hydrogen's heating value, we have to say it is the amount of heat that may be generated by complete combustion of 1 mole of hydrogen. Okay, which is around 286 kilojoule per mole. If it is, yeah. Okay, so that way this hydrogen's lower heating value is there, where we will have that the liquid water form will be the measurement will show that 241 kilojoule of heat is released, and this is known as hydrogen's lower heating value. Then what is hydrogen's higher heating value? The measurement should show that 286 kilojoule of heat is released. So where the heating value is done determined using stoichiometric requirement. If you have only the stoichiometric requirement of oxygen in the system, in that case what we get is a higher heating value. So the measurement will show around 286 kilojoule of heat is released, and this is known as hydrogen's higher heating value. So when you are combusting hydrogen with half molecules of oxygen in a calorimetric bomb calorimeter, and measurement of the heating value is done, we will get around 286 kilojoules of heat. Similarly, in the case where when we use excess air is used, or we can say excess oxygen is supplied, in that case in the same bomb calorimeter, when you measure the heating value of hydrogen, we will get a value lower value. Okay, so the measurement will show around 241 kilojoules of heat is released. So this is known as hydrogen's lower heating value. And the difference between two value is the heat of evaporation of water. The difference between the HHV, that is hydrogen's higher heating value, minus LHV, lower heating value, is the 286 kilojoule. When we are doing higher heating value, that is without excess oxygen, we got 286 kilojoule of heat is released. And when we do it with excess oxygen in the bomb calorimeter, we got 241 kilojoules. So this difference between 286 minus 241 is coming around 45 kilojoules per mole, right? So that is the heat of evaporation of water at standard temperature of 25 degree Celsius. Okay, and we have seen the theoretical electrical work, enthalpy. We have seen that delta H is delta H of product minus delta H of reactants. Entropy is given by delta S. For a closed thermodynamic system, a quantitative measure of thermal energy that is not available to do the work. It may be mechanical work or chemical work or electrical work, that is called as entropy. And in chemical terms, delta S is given by entropy of the product minus entropy of the reactants. Enthalpy is given by enthalpy of the product minus enthalpy of the reactants. Okay, so we have seen that delta Gibbs free energy is given by delta H minus T delta S. So this delta S is given by S of product minus S of reactants. So delta S is given by S of product. What is our product here? Water. So SF of water minus SF of hydrogen plus of SF of oxygen will give us the delta S value. Okay, coming back to Tafel reactions and Olmer reactions, we have seen what is open circuit potential. That is when any one of the component is absent, we have open circuit condition. Okay, absence of any of these components will lead to a condition called as open circuit condition, which means that there is no flow of current. Okay, so what is the global H2O2 reaction? Global redox reaction is overall reaction. Global redox reaction is given by, we know that of H2 plus of O2 gives H2. Remember, it is a reversible reaction. Okay, and what is the reaction at the anode? Reaction at the anode is given by H2 forms H plus ions and electrons. Balancing it, we have 2H plus plus 2 electrons. Okay, remember, this is the global reaction. Okay, global hydrogen electrochemical oxidation mechanism is given by global hydrogen electrochemical oxidation, HOR. Okay, we have discussed that in last lecture. Global H2O electrochemical oxidation reaction mechanism is given by, actually remember, even though it is simply written a single step reaction, this is overall reaction, this is the reaction taking place at the anode, right? So this global H2 electrochemical oxidation reaction mechanism is given single step here, but actually in reality it is very unlikely that it will taking place in a single step or single step reaction. It's not a single step reaction. Okay, and it follows two steps. Okay, so what are the two steps is, remember, any gas going and getting onto the surface of the solid, there will be adsorption taking place, right? So obviously a molecule will go and get adsorbed onto the surface, then the reaction will be taking place, right? So we are having two steps here where these H2 molecules will go and form HM. M refers to any catalyst, metal catalyst. Okay, catalyst layer or catalyst surface. Okay, and this is adsorption. It gets adsorbed. Okay, where M is the metal catalyst surface. Okay, and hydrogen dissociation or chemisorption step. Hydrogen dissociative chemisorption step, or it is called Tafel reaction. Tafel reaction. So what is happening in this Tafel reaction is, what is happening? H2 is getting into HM, right? What is happening there actually? The bond is broken. You can say the hydrogen bond is broken and a layer of atomic hydrogen is adsorbed on the catalyst surface. Is adsorbed on the catalyst surface. Okay, and this is step 1. Step 1 is dissociation of hydrogen molecule into atomic hydrogen and getting chemisorbed onto the metal catalyst surface. That is step 1, and which is also called as Tafel reaction. Okay, next, second step. Second step is given by, that is the one which is responsible for the actual charge transfer and the current generation. Okay, it is responsible for a actual charge transfer and current generation. Okay, so it is referred to as Olmer reaction. This reaction is referred to as Olmer reaction. What is formed in the first step? H2 becoming HM, adsorbed, chemisorbed. Okay, so this again a reversible reaction which will form H plus plus electrons. Okay, so this is the second step, and this is called as Olmer reaction. So two steps together, what we can write is H2 reversibly forming HM adsorption, then again they reversibly form H plus plus electrons. Okay, if you want to write it in this way, here we have tried 2 electrons because we consider H2 here. Okay, so this is what happens. Then if you want to balance this is 2. Okay, one molecule contains 2 atoms, so 2 atoms are getting adsorbed to the surface, and those adsorbed molecule undergo further reaction, Olmer reaction, to form this thing. So this first step is called as Tafel reaction, and is it possible to change color? Yes. And the second step is called as Olmer reaction. So this is called elementary local reaction. Local reaction that is taking place at the anode surface. Okay, at anode, global reaction is that one. What is that? H2 becoming 2H plus plus 2 electrons, which we think it is a single step, but actually this takes place in 2 steps. Okay, first step is hydrogen molecule becoming HM. Second step is this HM is becoming H plus plus electrons. Okay, both are reversible reactions. So together we can write with the balanced H2 giving 2HM and 2HM is giving 2H plus plus 2 electrons. Okay, so this is what happening at the surface of the anode. Okay, so this is the reaction that is taking place at the anode. Okay, and cathode, we know the reaction that is taking place, oxygen is getting reduced, okay, to form water. Okay, Now, coming to the thermodynamics part, equation of state. What is equation of state? They give the relationship between pressure, volume, and temperature. Okay, so equation of states provide the relationship between pressure, volume, and temperature in a system. Okay, because when you have a system, we are going to have a particular pressure, temperature, and volume. So these three are interrelated. If you change any one parameter, the other two will get changed. So what is the relationship? How they change is what we are going to learn in. We know about this in equation of state given by the thermodynamics. Okay. To start with the well-known PV equation of state is ideal gas law. Ideal by the molecule is 4 into 10 power minus 27 meter cube. Volume occupied by 2.4 into 10 power 25. That is volume occupied by molecules per unit volume is negligible. Okay. So that is what the assumption is, and at low densities, at low density conditions, what we have is PV equal to RT. Actually, PV equal to nRT. Okay. So volume V by N will give you this thing. Okay. So that is what ideal gas law gives us. Okay. So that means when you know any four parameter, out of four parameter, any three is known, you can determine the rest, where R is the universal gas constant that we know, right? 8.314 kilopascal meter cube per kg mole. Kelvin. Other units are also there. You can refer to the book. So R is universal gas constant. Okay, so when P, V, and T, if any two are known, the third can be determined. Okay, so that's what I told. For hydrogen and all, it is contained in a cylinder, compressed gas like the form, or even in liquefied form. We should be able to know the how much, what is the mass, if we know the pressure and the temperature at which it is stored. Okay, so that is one equation of state. We have another equation of state is van der Waals equation of state. What is van der Waals equation of state is, so we have seen some of the assumptions made in for molecular let me say B, which is equal to two times. Okay, one counting of each plus A by V square into V minus B equal to RT. Okay, and this equation is called as equation of state, which is your three equations. One is ideal gas law, Clausius equation, and then van der Waals equation. Using 3, 1, 2, and 3, we will determine the volume. Okay, what is the difference? What is the effect? We can be understood. Okay. Now, so we have seen the overall reaction that is taking place in a fuel cell. What is the overall reaction taking place in the fuel cell? Overall reaction taking place in a fuel cell is given by, so you know that one, right? So what is that? We have fuel plus oxidant giving, we are going to have an oxidation product. I'm writing general so that any fuel you can write. Okay, even for hydrogen, oxygen, or even if it is methane, we should be able to write these things. So fuel plus oxidant combines to form an oxidation product, plus from it does some useful work. It may be electrical energy. Okay, and also some heat is liberated. Okay, that is, let it be equation number 1. So we know what is the reaction if hydrogen oxygen is used as the fuel. So we know that H2 plus half O2 gives H2O plus electricity plus heat. Okay, 1A. And what if the fuel is methane? Let me say methane is CH4, right? So if fuel is methane, what will be the reaction? CH4 plus oxygen will form this oxidant product, and in that case water also will be formed, plus electricity plus heat. Okay, so if you balance it, what will happen? We are going to have 2H2O and 2 oxygen more. Okay, so this is the, we should be able to write the reaction with this thing in mind. Okay, so if you know this fuel plus oxidant plus oxidation product plus useful work plus heat will be there, we will be able to write whatever is the fuel given. You know that any hydrocarbon can be used, right? Any hydrocarbon or any gas, biogas is given as the fuel, we should know to write how to write the reaction and balance it. Okay, and we know that for hydrogen fuel cell, H plus ions will be flowing through the electrolyte from anode side to the cathode side, and we know what is the reaction taking place also, right? And hydrogen molecule is split into 2 protons and 2 electrons, and the electron will be flowing through the external circuit and to the positive electrode. Okay, it will move to the cathode, and at the cathode what is happening? The electrons flows through the external circuit to the cathode side. H plus ions moves through the electrolyte to the cathode side. Oxygen is freshly being supplied at the cathode side. So all these three will be entering at the anode. So we are having the reaction to form H2O. Okay, so that is the reaction taking place. Now looking into the what is the energy balance. If you look at the energy balance, so energy balance is, we are going, as I said, this, if you say H2 energy balance for H2O2 fuel cell. Energy balance for H2O2 fuel cell is, when we write, you can write H2 plus half O2 will form H2O plus E electrical minus E mechanical plus Q. Okay. Where V electrical is 2 electron volts. Okay. And E mechanical is your 1.5 RT. E mechanical is 1.5 RT. and Q is the rejected heat. Okay, Q is the rejected heat. So R is the gas constant, T is the absolute temperature in Kelvin. We get E mechanical, E electrical is 2 electron volts. Okay, so that is what we can write the energy balance. And we have seen that from thermodynamics in the previous lecture, we have seen that G equal to H minus T delta S. Okay, delta G equal to delta H minus T delta. Starting from G equal to H minus Ts, we differentiated with it delta G equal to delta H minus T delta S minus S delta T. But this term is 0 because isothermal condition. We are operating at a fixed temperature. So that's why we have this equation, right? So delta H minus T delta S, where H is the enthalpy in joules, T is the temperature in Kelvin, S is the entropy in joules per Kelvin. Units, we should know it's joules per Kelvin, temperature is in Kelvin, okay, H is in joules, okay. So we are doing this reaction at the constant temperature, so we have this condition, okay. So change in Gibbs free energy at constant temperature in a chemical reaction is given by this equation, okay. And by electrochemistry, we know that delta G is equal to minus NFE of the cell, okay, and it is a reversible one, okay, reversible reactions minus NFE, and E, here this E is not energy, whereas it is the potential in volts, okay. F is the Faraday's constant. You know the value of Faraday constant, okay, 96 point. Faraday's constant are the value of 96.487 kilojoule per kilomole. Accordingly, if it is per gram mole, you will be writing like without this point, okay. And N is the number of electrons taking part in the reaction. Number of electrons taking part in the reaction. Okay, so number of electron per mole of the fuel. Number of electron taking part in the reaction per mole of fuel. For 1 gram mole of fuel, how much number of electrons are involved? Okay, so that we have. So let it be equation number 1. Let it be equation number 2. So you can equate these two, right? And this effect of temperature can be taken into account if you are able to rearrange this equation, this delta H, delta S, all that, how to get those values. Okay. Delta G is equal to delta H naught minus T by T naught into delta H naught minus delta G naught minus delta Cp T into ln of T by T naught plus T naught by T minus 1. Okay. Where delta H naught is the enthalpy change at T naught. What is the T naught? That is 298 Kelvin. Temperature and pressure is 1 atmosphere. P naught, P naught is temperature and pressure at this condition, standard conditions. Okay. And what is delta Cp here? So here we are having a term delta Cp. This delta Cp is the change in molar specific heat in joules per mole Kelvin. Okay, joules per mole Kelvin in the reaction that is taking place. Okay. So change in molar specific heat is given by delta Cp equal to, here product is C of product, Cp of product minus Cp of reactant. Okay, so you can write delta Cp for this hydrogen oxygen fuel cell is delta Cp is equal to Cp of water minus Cp of hydrogen minus Cp of oxygen. Remember, only half mole of oxygen is used, so it is 0.5 Cp of oxygen. Okay, so this is what you will be making use. And change in Gibbs free energy is related to the maximum conversion of chemical to electrical energy. So this delta G what we have discussed is the change in Gibbs free energy and this change in Gibbs free energy is related to the maximum conversion of chemical to electrical energy. This chemical energy to electrical energy for the given reaction. So change in Gibbs free energy relates to the maximum conversion of chemical energy to electrical energy for a given reaction. Okay, so how you can relate? I just recall what we have discussed earlier. dg equal to dh minus t ds minus s dt. So that is negligible. So we can say dh is equal to du plus pdv plus vdp, and we have this du equal to tds minus we minus pdv. We can say dg equal to we. Okay. Well, what is heat of neutralization? Let me select the pen. What is heat of neutralization of an acid? We do this for an acid or base, right? What is heat of neutralization of an acid or a base? An acid, a base. Okay. It is the heat evolved when one equivalent of the acid or base is neutralized by a strong opposite one. If it is acid, it is neutralized by a strong base. If it is a base, it is neutralized by a strong acid. Okay. If it is acid, it is neutralized by base. If it is base, it is neutralized using acid. What is neutralization? We try to bring down the pH, right? Acid means less than 7. Alkaline means greater than 7. Okay, so bring it down the pH to 7, we do the neutralization. Okay, or even adjusting the pH among the alkaline condition itself from 10 to 8, you have to bring down the pH to 10 to 8. Again, we'll use the strong acid to neutralize it so that we bring down the pH. Okay, so it's not that always bringing back the pH to 7. It may be from 12 to 10, 12 to 8 also. Okay, so what is neutralization reaction that is taking place? For neutralization reaction, delta H of neutralization is equal to delta H of ionization plus delta H of H plus OH minus. Okay. What is heat of solution? Heat of solution is, it is the heat we are making. Say for we have a salt, we have water, we mix that salt into the water, we get a solution, right? To how we prepare a solution, I want 1 molar solution means I take certain amount of salt and dissolve it in distilled water or refined water. Okay, so this heat of solution is the heat evolved or observed. It is the heat evolved or observed when 1 mole of solute, we call it a solute, and the liquid is called a solvent, right? So the heat evolved or observed when 1 mole of solute is dissolved completely in the solvent. Okay, so that is the heat of dissolution or heat of solution. What is heat of hydration? Heat of hydration is heat of hydration. It is a heat. It is a heat accompanying the formation of 1 mole of hydrate from 1 mole of an anhydrous substance on combination with required number of moles of water. Can you give some examples of sulfate? Sulfate hydrates are there, anhydrous sulfate solutions are there. Okay, so sodium sulfate are there, kind of thing. So you'll be able to make hydrates. At that time, what is the heat accompanying the formation of 1 mole of hydrate from 1 mole of anhydrous substance on combination with the required number of moles of water. Okay, and we can give some examples. Write 5 examples for that. Hydrates formation. How many hydrates can be written? Okay, so then coming to some of the laws of thermochemistry. Coming to the laws of thermochemistry, we are going to discuss about 2 laws. One is Laplace law, another one is Hess law. Okay, what is Laplace law? It tells about, we have a Laplace law. Okay, what is this? Laplace law states that heat evolved in a chemical reaction. Heat evolved in a chemical reaction is equal to the heat observed when the reaction is reversed. Okay, that means forward reaction is there. If delta H is something, some X value, when during the reverse reaction, the delta H will be minus X. Only that minus sign is used to represent the direction is opposite. Okay, but the magnitude is same. If it is 100 kilojoule per mole, so in reverse also it is going to be 100 kilojoules per mole. For forward reaction, if it is plus, for reverse reaction, it is going to be minus. That is the only different. That's what Laplace law says. Okay, so then we have Hess law. It's very important. We will be making use of this. Okay, so Hess law states that if A is forming B, B is forming C, and C is forming D, then if A is directly formed in the form of D, then if for this reaction let delta H is equal to Q, then for if it is a multi-step reaction, the heat of formation is either Q1, for this reaction it is Q2 and Q3. So if it is A giving D or A directly giving D, that is when a product is formed through multiple steps or single step from the same raw material, the heat of the reaction is same. Or you can say it is just like a special case of first law of thermodynamics. Okay, first law of thermodynamics. Okay, so it is a special case of first law of thermodynamics where when A is directly forming the product D, if the rate of the reaction is the delta H is Q, and if A is giving B, B is giving C, C is giving D, where Q1, Q2, Q and Q3 are the respective heat of the reactions, then we have, according to Hess law, states that this Q is equal to Q1 plus Q2 plus Q3. Okay. So this is the Q, and this is your Q3, Q2, and Q1. Okay. So if a reaction is taking place in single step or multiple step, you are going to have the from the raw material to the product, the delta H is the same. Okay. So that's what Hess law states. Then we have what is heat of formation. What is heat of formation of a compound? That is a mixture product. We form a product. What is the heat of formation of product? It is a heat change accompanying the formation of, it is a heat change accompanying the formation of 1 mole of the compound from its elements under standard conditions. Okay, so for example, we are going to consider several hydrocarbons in our case, right? Let us say CH4. If you consider, you can say formation of methane. Okay, we can say CO2 formation is there. You can say formation of CO2. So what is the heat of formation? For example, if from its elements we have to form. Okay, so CH4 is formed means how we will get, if we want to know CH4, how it can be formed from its elements, we have to balance it. C plus H2, 2H2 gives CH4. So we are going to have delta H of formation equal to say minus 18.5 kilocalories. You can write in kilojoules also. Okay. Similarly, CO2 has to be formed. Then from its elements, C plus O2 forming CO2. So delta H of formation is equal to minus 96.96 kilocalories. Okay, per mole. For example, 1 mole of methane formation. If 10 mole is formed, delta H of is equal to 10 times this. Okay, so that is why we can calculate this thing. So this is heat of formation of a compound. And what is heat of combustion? Heat of combustion. Actually, it is reverse of heat of the reaction. In place of reaction is a combustion reaction. In that case, it is heat of combustion of a substance. Heat of combustion of a substance. Heat of combustion of a substance or a reactant right? Reactant is combusted, right? We don't say product is combusted. Coal is combusted, we say, right? So that way, the heat of combustion is defined as the heat evolved when 1 mole of that compound or reactant is burnt with oxygen. Completely. Is completely burnt. With oxygen. So example is, we can heat of combustion of hydrogen. Hydrogen can be combusted, right? H2 plus of O2 giving H2O is again a combustion reaction if it is combusted. Okay, so you can say heat of combustion of sulfur, S plus of O2 gives SO, or S plus O gives SO2. Okay, so for example, this reaction, what is your delta H of combustion? So your delta H of combustion for this reaction 1, let me say reaction 2. So for reaction 1, we have delta H equal to minus 68.4 kilocalories. And for the reaction 2, delta H equal to minus 71 kilocalories. Okay, so when we are doing combustion reaction. Okay, so if they are combusting, this is what happens. How will we measure this? Generally, these are measured using bomb calorimeter at a constant volume as delta E, which is converted to delta H. So because we know that delta H equal to delta E plus delta N RT. Okay, so when all the reactants are in the solid or liquid phase, we have delta N equal to 0. Okay, if it is same phase, we have delta N equal to 0. Okay, where delta Ng is moles of gaseous product minus moles of gaseous reactant. If all the reactant and products are only solid or liquid, in that case delta Ng is 0. Okay, and no gas reactant or product is there, in that case delta Ng is 0. Okay, that is about heat of combustion. And coming to the heat of the reaction, so we know that heat of the reaction is the energy input equal to energy output plus losses. Okay, heat capacity of, what is heat capacity? At constant pressure for any gases, the heat capacity at constant pressure is given by Cp is equal to A plus Bt plus Cp square plus D into T cube. Okay, this A, B, C, D are constants. Remember from literature or even from Perry's handbook or any thermodynamic books, for any substance you will able to get A, B, C, D values. Okay, so for a Cp value, okay, heat capacity. And heat capacity of a gas mixture is given by how we get the heat capacity of the gas mixture. It is Cp mean value of a gaseous mixture. If there are I components are there, that is 1, 2, 3 up to I, we can get Cp mean equal to summation of Xi into Cpi, where Xi is the mole fraction. And 1 and Cpi of the ith component. Cp is the heat capacity of ith component. Okay, so that way, based on the proportion, if for example air is there, okay, air contains nitrogen and oxygen in 79 mole percent, 21 mole percent. Okay, and Cp of nitrogen is known, Cp of oxygen is known. Okay, so how will you get the Cp mean value? You get Cp mean value is equal to 0.79 into Cp of nitrogen plus 0.21 into Cp of oxygen. So that way we'll get the heat capacity of a gaseous mixture. If it is air, we know how to calculate this one. Okay. So enthalpy changes when you are coming with, now we are coming to this heat of the reaction. When enthalpy changes with chemical reaction, we are going to have different conditions. We'll see. So delta HR naught, what is that? This is the standard heat of the reaction at 25 degrees Celsius, that is 298 Kelvin. Okay, and delta HF is the standard heat of formation at 25 degrees Celsius, and delta HC naught is standard heat of combustion at 25 degrees Celsius. That way, we will be writing delta H value, enthalpy change only. Okay, so the enthalpy change with the chemical reactions enthalpy change with chemical reactions can be written by delta HR naught, delta HF naught, or delta HC naught based on whether it is a reaction, whether it is specifically a combustion reaction or it is formation of a compound. Okay, and we can write for any reaction delta HR naught is equal to summation of delta HF of the products minus summation of delta H of the reactants. Okay, so this is what is this enthalpy of products at 298 Kelvin, and this is enthalpy of reactants. So you can say enthalpy change of a chemical reaction is given by enthalpy of the products minus enthalpy of reactants. Okay, so summation of when more than one reactant and more than one product is there. Okay, so here only we are going to make use of Hess law. Okay, so Hess law is used to for the heat of combustion of any substance can be calculated. Okay, from the heat of formation of the reactant and the products. I repeat, heat of combustion of any substance can be calculated using the data of heat of formation of the reactant and the product. Okay, so now we should know that when liquid water is the product, we are going to have a higher heating value, and when gaseous water or vapor gaseous form of water is vapor. Okay, when water vapor is the product, we are going to have a lower heating value. And the difference between this higher heating value and lower heating value is higher heating value minus lower heating value is the nothing but heat of evaporation. Okay. So for example, if it is water, we can say that 286 kilojoules minus 241 kilojoules given by 45 kilojoules per gram mole is the heat of evaporation of water. Okay. So that way we can get the heat of the reaction or heat of evaporation. Everything can be calculated. Okay. Now we have a table of enthalpy and entropy of formation. For hydrogen we have a value, for oxygen we have a value, for water in liquid form we have a value. Okay, water in gaseous form we have a value. And what is heat of formation, that is in kilojoules per gram moles. For pure elements we should be able to write immediately 0 0, right? And if water is in liquid form, we have minus 286.02 kilojoules per mole. If it is this, 241.98 is the one. Similarly, we should be able to write for methane, methanol, because we are going to use other fuels also. Okay. So please write those values. So please fill the value for this heat of formation. Similarly, we have entropy formation. What is the entropy of formation? It is SF. It is also in kilojoules per gram mole Kelvin. Okay, unit you have to be aware. SF, which is written in kilojoules per gram mole Kelvin. So we have the data for hydrogen. We have 0.13066, for oxygen 0.20517. I'm just giving a average value. For specific numerical, you will get the value correctly. Okay. If not given, you can use the value given here. Okay. Please complete this table by referring to the literature. Okay. Concept that even though we have learned them earlier also, I just have to refresh all these concepts of what is the equation of state from thermodynamics, what is Laplace reaction, Olmer reaction, what are the laws of thermochemistry like Laplace law, Hess law, heat of formation, heat of reaction, heat of combustion, heat of evaporation. So all these concepts are important to solve the numericals. We have discussed about this equation of state because hydrogen is stored in a cylinder, so we should be able to calculate the mass, volume for a given pressure and temperature. We have to even discuss the effect of temperature, how the Cp values, entropy values, delta H values are changing with respect to temperature, and then we'll solve numericals. Okay. So then we will solve more numericals to determine entropy, energy loss due to entropy, effect of temperature, delta S, delta H, effect of pressure, theoretical efficiency, all that in the next lecture. Okay. Thank you so much for joining my classroom. Meet you in the next lecture. Bye bye.